Oops. I'll be there in just a second. I'm just trying to set up a second screen here.
Hey, Professor Ordewer, is there a password for this meeting? Sam was just asking me.
Yeah, it's 3353.
Okay.
It's the course number.
Just a little bit. Oh, I thought that was 300%.
So, hang on just a second. I'm using a very clumsy system right now. I'm gonna have to figure this all out. There we go. So after I made the recordings of the session on Monday, oops. I realized that everything was in, what do they call it, gallery mode, where everybody's picture was the same size. Now, I didn't really use the Blackboard much on Monday, so it didn't matter much for this class. So now as I'm making the recordings, I am pinning my picture to the screen, which means I can't see most of you on this screen. So I have a second screen set up over there where I can see all of you in gallery mode, but this is really very clumsy right now. I'm gonna have to figure out a better way of doing this so that I can record and you can see what's on the Blackboard and I can see you, and I'll get it right, and I hope you'll be patient with me until I do. So in Monday's class, I gave out a number of problems which we worked on in groups. I don't know, has anybody been working on those since Monday, or you just, I didn't ask you to. I'm just curious as to whether anybody did. Okay, that's totally fine. I didn't actually intend anybody to work on these things between now and between Monday and now. I just wanted to get some sort of feel, but I did want to start putting this stuff into context. What we have here is these are systems which change dynamically. They evolve over time. So these rabbit problems, yeah, that's what we have here. You have rabbit problems mostly. And the population of the rabbits evolves over time. I want you to notice certain specific things about what we're doing in these particular problems. Note, time is discrete. T equals time 0, time 1, time 2, time 3. These are discrete numbers. We're not worrying about time 2.5 or time pi. So we're treating time as if it was discrete here. Our populations are discrete. According to this model, the populations are whole numbers. So in these models, populations are whole numbers. Times are whole numbers. So it's sort of discrete time, discrete position, if position means population in this case. Can I just see from a show of hands how many of you have taken, and I don't care whether you have or you haven't, it's not a prerequisite for this course, but how many of you have taken, say, differential equations? Anybody? One?
I'm currently taking differential equations.
Or are currently taking. So have taken it or are taking it now. So 2 of you. So differential equations is built on top of calculus. When you do a differential equation, so calculus is all about nice, smooth, continuous functions. Here, now you can see my hand waving. So calculus is all about nice, smooth, continuous functions. When we have time in calculus, time varies continuously along a scale, right? We have, here's time equals 0, here's time equals 1, but time equals a half is somewhere in between. And time equals 2/3 is somewhere between a half and 1, and so on. So time varies continuously on a scale. And when we use calculus to build models, in other words, if we're going to have like a dynamical system using calculus, it's going to have continuous time generally. And it'll have continuous position. If I have a rocket and its acceleration is blah, 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 these are all calculus problems or elementary physics problems. It starts off at height 0. It starts off, at velocity 0. Find the height after t seconds. T is a continuous variable there. It is not a discrete variable as it is in this case. And we will talk about continuous variable problems later on in the course because they're just as useful as discrete model things are. There are models where it makes more sense to treat time as if it were discrete. If I'm doing things by years, it makes sense to treat time as if it were a discrete thing. If I, so we're talking about, let's see, what's something where it makes sense that, let's say some animals basically only have babies in the spring. It makes sense to talk about the population once a year because basically all the being borns are being done at one time a year. There are times where it makes much more sense to talk about time as if it were a discrete variable. But right now, these models have discrete time and discrete whatever it is we're talking about. In this case, population, but we could be talking about position or temperature or whatever. So everything is discrete right now. In problem number one, so problem number one. We have a single pair of rabbits. So we'll chart like this last time, is in years, number of pairs of rabbits. It made sense to talk about pairs. And we said in time 0, there was 1 pair of rabbits. And a pair of rabbits gives birth to 1 pair of rabbits, 1 male and 1 female, very convenient, every year, beginning at 1 year of age. And these rabbits are immortal. They're immortal rabbits. I don't know how I feel about immortal rabbits. So let's define some variables. Let's let t be time in years. And let's let p, or p is a function of t, so I can write p or p of t. It's not p times t, it's p of t. The way you write functions in a pre-calculus class or in a calculus class. This is just the population at time t. And again, I want to reiterate that right now we are treating time as if it were a discrete variable, t equals 0, t equals 1. There's nothing in between that, as opposed to what we would do in calculus where we have sort of the continuous number line. And I'm not saying this course, I don't want to give you the idea that this course is only a course where we're treating variables as discrete. It's certainly not the case. We will treat variables as discrete sometimes, in some models, and continuous in other models. I would just like it to be clear in your head when we look at a model, what kind of model we're looking at. So let's see. One thing I didn't ask you about, I mean, I did ask you in part A to figure out the number of pairs of rabbits for the first 8 years. So I think everybody sort of managed that. After 1 year, there were 2 pairs of rabbits because the first pair had babies. Now there's a second pair, and after the second year, the pair that was born, that was born in year 0, the pair that were born in year 1 each had a pair, so there were 4. And third year there were 8, and this gets pretty boring after a while. But we could continue that for 5 more rows if we want. So let's see. Let me ask you something that I didn't ask you. How does t of t plus 1, the population at time t plus 1, relate to the population at time t? How are those two things related, according to the problem?
Professor Order.
Yeah.
Sam said, could you let him in the meeting?
Oh, yes, absolutely. Okay, we good?
Yes, sorry.
No, it's all good. And as I said last time, I'm trying to figure out, I did put a password or whatever it's called, an entry key for this room. So I should be able to turn off the waiting room and have you come in directly. I need I think the way Zoom is set up, I need some kind of security, but it can be password or, are you all typing in the password when you come in?
Yeah.
So you all know the password. It's just the course number. It's just 353. So I think if I turn off the waiting room, that you can come directly in. I will try that hopefully for next class. I'm still trying to figure out exactly the ins and outs of Zoom. I used it for office hours last semester, but there are plenty of things about Zoom I don't understand all that well yet. So I'm still working on that. So I think if I turn the waiting room off, you can come directly in. And the way I have the settings set up, you should be able to get it here before I get in here. So you should be able to come in whenever.
Cool.
So let me come back to this question. How does the population at time t+1 for this particular problem number 1, relate to the population at time t?
It's doubled.
Okay. How big is the population at time t? So the population, writing this out in terms of a formula, p of t plus 1 equals 2 times the population at time t. For those of you that have taken Math 234, Introduction to Mathematical Proof, can I just see a show of hands? How many of you have taken that course? 1, 2, 3 and a half. I can't tell. Yeah, 4. Right, so about 4 of you. So you've seen things like this before. These are called recurrence relations. If you know what P of t is, you can use this recurrence relation. If you know what the population at a certain time is, you can use this recurrence relation to figure out what the population at the next time is. So let me just put a couple more rows in here. 4 at time 4, there are 16 pairs of rabbits. At time 5, there are 32 pairs of rabbits, and so on. Can you give me a formula for P of t using t as a variable? I mean, I'm sure you can. Would you? What might that formula be?
2 to the t.
2 to the t. So P of t is just 2 to the t. 1 equals 2 to the 0. 2 equals 2 to the 1. 4 equals 2 squared. 8 equals 2 cubed, and so on. This is called a formula for P in closed form. So here P is at least as big as 0. I could have just as easily written this as P of t equals 2 times P of t minus 1. The population so these two are, hopefully everybody realize are equivalent. This here, t is at least as big as 0, and here t is at least as big as 1, because I can't have population at time -1. T has to be at least as big as 1 for t minus 1 to make sense in this problem. T equals 0 is when the whole thing starts. These two are equivalent. This is equivalent. Sorry, I am struggling with the Blackboard limitations. So here we have a formula for P of t. 2 times P t minus 1, that is a recurrence relation. And here we have a formula P of t equals 2 to the t. This is in closed form. Hopefully, we can consider the various merits, what's better about each one of these forms. A recurrence relation is often easier to find. Whoops. Than a closed form. That's the advantage of a recurrence relation. Basically, this is just a rewording in algebraic jargon of what is said in the problem. So the population basically doubles every year. But this, the closed form, has a huge advantage. What's the advantage of the closed form over the recurrence relation?
Simpler?
In this case, it is. It's not always. That's a good observation that in this case, it happens to be simpler.
Is it, you can know the population at a time without knowing the population at a previous time?
Yeah, if T is large, then computing the population this way, let's say I want to know the population at time 1000. Well, first I have to work out what the population is at time 1. And then what's the population at time 2, and then the population at time 3, and so on. And I have to go all the way to 1000. Here, it's just one computation. So the closed form allows us to compute the population at any time without computing the population at previous times. So we have two forms of a model here. They describe basically the same model. This is easier, and this is easier to find, and this is certainly easier to work with, especially for large T's. So oftentimes, you have a problem. If the problem is a problem like this, you start off with the problem. You can come up with a recurrence relation. And then you come up with a closed form. For those of you who are taking differential equations now, for those of you that take differential equations in the future, basically, there's the equivalent thing. You have a problem, you come up with a differential equation, and then you solve the differential equation. It's the same thing. Let's take a look at the problem in number 2. Let's see. We're going to repeat problem 1, except a pair of rabbits gives birth to 1 pair of baby rabbits every year, beginning at age 2 years. So you have this P of T. Hang on, let's define some more variables. So T will be time. Let's let P of T be the number of baby rabbits at time T. Let's see, year-old rabbits. What do we want to call those? Like, we'll let Y of T be the number of year-old rabbits. And we'll let A of T be the number of adult rabbits, at least 2 years old. So B, Y, and A. Baby, just born, Y, year old, a 2 years old or more. And these rabbits, like the rabbits in problem number 1, are immortal. And P of t will be the total population of rabbits. P of t is the total population of rabbits. That's going to equal the number of babies plus the number of year-old rabbits, these adolescent rabbits, plus the number of adult rabbits. So let's make up a big chart. So let's see, baby rabbits, number of baby rabbits, number of these adolescent rabbits, these year-old rabbits, and the number of adult rabbits, and then the total population of rabbits. Just to save writing, I'm not writing B of t, Y of t, A of t, I'm just suppressing the of t. So in year 0, we introduce one set of baby rabbits. There aren't any adolescent rabbits, and there aren't any adult rabbits, and so altogether there's just one pair of rabbits. So after 1 year goes by, these babies are not old enough to have babies yet, but they did age. They aged by a year. There are no baby rabbits right now. They aged by a year, so that one goes right there. No adult rabbits yet. Still one pair of rabbits. In year number 2, these rabbits are now 2 years old. There aren't any year-old rabbits. 2 years old, that's old enough to have babies in Rabbitland. So now we have a pair of baby rabbits. One pair of babies plus one adults, 2 total pairs of rabbits. Can everybody take a couple minutes and write a few more rows here?
Yep.
So in the 3rd year, this pair of baby rabbits ages. We have a pair of year-old rabbits. Let's see, we still have one pair of adult rabbits. Once they're here, they stay here. And this pair of rabbits is old enough to have a baby. So we have babies. So there are 3 here. 1 plus 1 plus 1 is 3. In year 4, this pair is now over here. So now we have 2 adult pairs. This pair is now over here. So we have 1 right there. These 2 pairs are each old enough to have babies. So there's 2 over here. So that makes 5. In the 5th year, we have, let's see. This pair has now moved over here. There are now 3. These 2 have moved over here. These 3 are old enough to have babies. 3 more sets of babies. And so now there are 8. Let's do another row. In the 6th year, this pair has moved over here. 5. This pair, these 3 have moved over here. 3, these 5 are old enough to have babies. So there are 5 babies. And so 5, 13, and so on. There are really a number of interesting observations you can make once you have that chart all together. One observation that a lot of you made last time is that these numbers over here, 1, 1, 3, 5, 8, 13, and so on, these are the Fibonacci numbers. Oops. By the way, this is exactly the problem that Fibonacci was working on when Fibonacci discovered the Fibonacci sequence. By the way, his name wasn't Fibonacci. His name was actually Leonardo, and he lived in Pisa. This was not his greatest contribution to Western mathematics. Actually, his greatest contribution to Western mathematics had nothing to do with this particular sequence at all. His father, whose name was Bonaccio, was a merchant, and Fibonacci traveled with him. At the time, Europe was not counting like this. 1, 2, 3, 4, 5, 6, 7. They were counting using numerals like this. And so on. Roman numerals. This was what was going on in the 11th century in Europe. Have any of you ever tried to do arithmetic with Roman numerals?
No.
Good. Torture. It's
Yeah.
it's ridiculous. There's no point to it, which makes me wonder if my teacher was just trying to make a point. Anyway, so it's very difficult. But Bonaccio traveled because he was a merchant, and he took his son Leonardo with him. And one of the places they traveled was North Africa. And in North Africa, we have lots of trading by the great Arabian trading, society. And they were already using this set of numerals that was originally invented in India. These are sometimes called Arabic numerals, or the Hindu Arabic numerals. It was originally invented in India, picked up by the great Arabic trading culture, and eventually Fibonacci picked this up, and he wrote a book and popularized it in Europe, which is good because the Renaissance could not have occurred if you were still trying to do arithmetic this way. You couldn't have done all the advanced science and architecture and astronomy and various things that happened during the Renaissance very effectively if you were using Roman numerals. So this was very important. But Leonardo eventually just became known as the son of Boccaccio or Fibonacci. That's where we get the name Fibonacci, son of Boccaccio.
Oh.
Anyway, back to the problem. So you notice that this was the Fibonacci sequence. What are some other things you notice about this?
It's the number of new babies is equal to the number of adults every single year.
Number of adults. What do you notice about the column of the number of adults and the number of new babies also?
The Fibonacci numbers.
Yeah, the Fibonacci numbers again, it's just they're well, at least the number of adults is. The number of babies is messed up by this initial pair of babies. But if you ignore this, you ignore this, we have basically just the Fibonacci numbers all the way down. So there's just a bunch of Fibonacci numbers translated. So let's say this is the 0th Fibonacci number. This is the first, this is the second, and this is the third, and so on, 4th, 5th, 6th. So this is the Fibonacci, this is, P of 0, P of 1, P of 2, P of 3, P of 4, and so on. How do you figure out, how do we compute the population, the Fibonacci number at time n in terms of populations at previous times? In other words, what's the recurrence relation? We had a recurrence relation last time. The population at time n was just 2 times the population at time n minus 1. What's the population for the Fibonacci sequence? How do you get 3 in terms of the numbers which come in front of it? How do you get 5 in terms of the numbers which come in front of it? Yes, Jackson.
It's Pn minus 1 plus Pn minus 2.
Yeah, that's all it is. Population at time n is the population at the previous time plus the population at the time before that. Two equals 1 plus 1. 3 equals 2 plus 1. 5 equals 3 plus 2. So 2 equals 1 plus 1. 3 equals 2 plus 1. 5 equals 3 plus 2. 8 equals 5 plus 3. Whatever. If you know, let's say we know this. If I want to know what the population is at time 7, I'll just take the 13 and the 8 now, and I get 21. If I want to know what the population at time 8 is, I'll just take the 2 previous numbers, 21 and 13, and add them and get 34. So I have a recurrence relation. It's generally not hard to find recurrence relations. We said it was generally much harder to find a closed form. Is there a closed form for the population at time n? Here's a hint. Yes. However, how we actually work it out is not really part of this course. We can talk about it if you're interested, but the technique that you learn to do this is not really part of this course. For those of you that have taken a course, Math 234, whether it was called Discrete Mathematics when you took it, or whether it was called an Introduction to Mathematical Proof when you took it, you would have seen a technique for computing the closed form of this using something called a characteristic polynomial. It's very interesting. It's an interesting thing, and you can look it up, but I'm not going to reteach it right now. But so the answer is yes, and the form of the closed form may surprise you. Let me just go ahead and look it up for you. I've more or less pulled it up already. Let's see.
Did Fibonacci himself find this closed form?
I believe the answer to that is no, but Fibonacci realized, and I'm not positive about that. I don't think Fibonacci had the whole closed form, but Fibonacci realized something very interesting about the Fibonacci sequence. Hang on, I don't see it on this page. Fibonacci sequence. Let's see, closed form. Oh yeah, not until the 1700s. So not until about the time of the American Revolution.
Wow, that's insane. A couple 600 years to find it.
Well, some things take a while. Everybody has a part of it. Oh, for goodness. Just give me the closed form already. Oh, here we go. So population at time n is 1 over root 5 times 1 plus root 5 over 2 to the n minus 1 over root 5 times 1 minus root 5 over 2 to the n. Let's just double check and make sure that that works out okay for the first two numbers. So hopefully I copied it down correctly. So P of 0 should be 1 over, that's not going to work out right, is it? It'll be 0. Let's try P, let's do P of 1. Maybe this is supposed to be n plus 1. 1 over root 5. Let's see what it is for 1. 1 plus root 5 over 2 to the 1, which is just 1 plus root 5 over 2 minus 1 over root 5, 1 minus root 5 over 2 to the 1. So we have, let's see, 1 over 2 root 5 plus 1/2 minus 1 over 2 root 5 plus 1/2. So those cancel. 1/2 plus 1/2 is 1. So this must be n plus 1. There we go. So P of 0 now will be this. Equals 1. If we plug 1 in, I don't really want to plug 1 in because I square all that. But hopefully it should be 1 And if I plug 2 in, it should give me 2. If I plug 3 in, it should give me 3. And if I plug 4 in, it should give me 5. And 5 in, it should give me 8. It should give me all those numbers. But this may not be the form that you were imagining. For one thing, it has all these irrational numbers in it. Does anybody recognize this irrational number, 1 plus root 5 over 2?
Kind of looks like a quadratic.
It's definitely the solution of a quadratic. It's the solution to this quadratic. X squared minus x minus 1 equals 0. So this and this are both the solutions of that. But this particular number has a name. Has anybody heard of the golden ratio before? The golden section?
Yeah, it's the that's the ratio that most like Western buildings are built in, right?
Yeah, it's supposedly the ratio that is most pleasing to the human eye. Whether or not that's true, I don't feel qualified to express an opinion on. For a long time, they thought it was a part of ancient Greek architecture. Modern studies have shown no, not really. They thought like this was uh, the golden section was part of the Parthenon and part of high classical Greek architecture. But it is used in modern architecture a lot. They also thought it was very prominent in Renaissance painting, and most modern art historians think that that is not quite true either. Yes, Jackson.
Um, I wasn't aware of that, but from what I had known that there was like the golden and the silver ratio, and the golden ratio was more prominent in like Western style buildings, and the silver ratio was more prominent in Eastern style. And one of the theories of that was because of like the shape of people's faces, like people in Asian countries had like rounder faces, so it was like a different ratio. I don't know. I am getting all this from a video game, honestly.
No,
It's a piece of trivia from a video game.
no, I understand. And there are a lot of things that we formerly believed about the golden section and its relationship to architecture and art. The silver section, which further study have shown are not quite as cut and dried as we once thought. It's not quite as true as we once thought. But I also first inherited information about the golden section and the silver, well, not the silver section, but the golden ratio, not from a video game, because video games were at least, not very common when I was a kid, but from an older form of video in the form of an old Disney production called Donald Duck and Magic Land. I don't know if any of you have ever seen that. You can still locate it on
I
YouTube.
think I actually watched that in elementary
I
school.
wouldn't be surprised if some of you have actually watched it at some point in your lives. In some ways, it hasn't aged all that well. And certainly it has some information in terms of the golden ratio, the golden section, which is no longer considered to be true. One thing that surprises me about this formula that what we have here is you have all sorts of irrational numbers floating around. And yet when you plug in like whole numbers here for n, all the irrational stuff, all the square root of 5 stuff cancels out for every single n. Isn't that remarkable? It gives you a whole number for every single n. It gives you these numbers, 1, 1, 2, 3, 5, 8, 13. I find that pretty remarkable.
Who found this closed form? Like, do we know, or like?
Yeah, hang on. I just forgot.
Oh, sorry.
No. These are all good questions. This is interesting stuff, I think.
Relation number.
Let's see. It was found by. Oops. Did I see it? here we go. Closed form. Sorry. Binet. Yeah, it's found by Binet and around the American Revolution, I think 1786. So a little after the American Revolution. Yeah, so what Fibonacci did realize is that this had something to do with the golden section. This number, 1 plus root 5 over 2, that's about 1.61. You can work it out. But if you take a look at successive ratios of successive terms of the Fibonacci sequence, so let's take this divided by that. 1 over 1 is 1. 2 over 1 is 2. 3 over 2 is 1.5. 5 over 3 is 1.6 repeating. 8 over 5 is 1.6. 13 over 8. Let's see. 8. It's 1, 5. 1.625. So remember, we said the golden ratio. If you work 1 plus root 5 over 2 out, it's 1.61, whatever. But look at these numbers. 1, which is below that. 2, which is above. 1.5, that's below this again, but closer. 1.6 repeating, that's above again, but closer. Below again, above again. You take successive ratios, it's below, above, below, above, below, above, getting closer and closer to the golden section. The golden section was already understood by the Greeks. It was certainly understood by Fibonacci. And Fibonacci was studying this sequence. Fibonacci noticed there was a relationship. Fibonacci did not come up with this. The algebra that this depends on hadn't really reached Europe yet. Algebra was only like 100 years old at that point, and it was still in the Middle East. It hadn't hit Europe yet. Anyway, I have gone 2 minutes over. I apologize for that. And I spent more time talking about the Fibonacci sequence than I intended. It's interesting stuff.
Worth it. Definitely worth it.
I love this stuff. I mean, if this were a different course, I could spend the whole semester talking about this, but no. Any questions? Just looking at your faces right now. I will get this screen thing ready so I can talk to you and see you at the same time. But I have not managed that yet. Okay, well, bye everyone. See you Friday. There probably will not be homework posted tonight. I probably won't post it until Friday.
Bye.
Cool.
Bye now.
Do we have homework posted Monday?
Oh, what? Who said that?
Wait, did we have homework posted Monday?
Oh, no, there was no homework posted Monday.
Okay. All right, just making sure.
Yeah.
All right, thank you.
You're welcome.
And you say your lectures are recorded. Where would we go to rewatch them again?
They'll be on the same web page where you download homework. So the web page I told you about last time, if you go to http://faculty.randolphcollege.edu.
Okay, yeah.
And then just click on our course page, and then everything is there.
Okay, thank you.
But please do come to class. So attendance in class, unless there are extraordinary circumstances. I mean, if there's a conflict with a job or something, let me know in advance. And
Okay.
yeah, but for purposes of review and things, they'll all be online.
All right, thank you.
Welcome.
So, do we have senior sem this afternoon?
Yes.
Okay, I was making sure because your link meant what for Zoom was for this afternoon, but then when you sent the problem information, it was for tomorrow afternoon, and I was
No, that was a different course.
Oh, different. Okay, that's
That's for the problem solving seminar, which
Okay.
you're not obligated to come to. I sent that to every math major and people who I thought would be interested in the problems.
Because I was like, oh no, I'm in another class at that time. Like, is that going to be an issue? And it's like,
No,
okay,
no, no,
cool.
no, 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 no. Yes, I just thought you might be interested in the problem, so I sent them to you.
Okay,
Yep.
Awesome,
This afternoon's
thanks.
course is different.
all right, cool.